Software Engineering Radio Episode 88, The Singularity Research OS with Galen Hunt.
This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for supporting the podcast. Hello, this is another episode of Software Engineering Radio. Please take a look at se-radio.net and specifically at the link that leads you to the SE Radio Get Together, our 2008 Open Space meeting. It'll happen near Zweibrücken, Germany, October 16th and 17th. It's co-organized with D. Verlag. We would like to see you there. Please go to the website, look at the PDF, and consider coming. Another thing I want to briefly talk about only in this episode is that we'll have a little BOF, Birds of Feathers sessions, at QCon in London. QCon is actually next week from March 10 to, 14 or something. And on the Thursday evening, between 7:30 and 8:30 p.m., we'll have a little, we just meet and talk a little bit about SE Radio, give us feedback, announce some additional episodes, and just, talk a little bit about things. If you're at QCon, you're obviously invited to join. Thanks Michael Hunger for actually organizing this. So maybe see you there. Thursday, 7:30 to 8:30 in room 1, whatever that is. I guess we'll find out once we're at QCon. Okay, let's get ahead with the actual episode. This is an episode that's somewhat special because, first of all, it's a research topic we are talking about. And the other thing is that I'm actually at Microsoft Research, the first time I've ever been there. So the episode is about the Singularity operating system research project, and we're talking to Galen Hunt. So welcome, Galen, to the show.
Oh, thank you very much, Marcus.
So why don't you introduce yourself a little bit to our listeners?
So I'm Galen Hunt. I run the Operating Systems Research Group here at Microsoft Research in Redmond. I've been at Microsoft Research about 10 years. Before that, I was at the University of Rochester, where I did my graduate degree. And my primary interest is around operating systems, but I've done some distributed systems and a few other things. I spent most of my 10 years here in research, but I did spend 4 years of my time at Microsoft in the 2.5 years, in the Windows Server division as well.
Can you give us a 1-minute overview of what is Singularity in a nutshell? And maybe how is it different from traditional operating systems such as Windows?
So in a nutshell, Singularity is a brand new operating system. It's a research prototype that we've built from scratch in using managed languages. So C#, in particular, C# and other languages. Singularity is a microkernel type architecture, so it's very similar in that way. But the key idea is to see if we could build an entire operating system out of safe code from the ground up, and to see how aggressively we could use tools and language and operating system architecture innovations to allow us to build a system that fundamentally we could check for errors before we ever shipped the code, rather than try to test them out.
So the problem we want to solve is stability, reliability, dependability, or how would you phrase that?
So the way I describe it is dependability. And the simple way I describe it is, how do you make a system that has predictable behavior? Because if you think about what users want when they say dependable, they mean I know what it's going to do, and I know how it's going to react, and it's going to meet my expectations.
Maybe before we go to the solution approach and the patterns and the stuff you did, why are traditional operating systems not dependable? What's the problem? Is it just history? It just became like that, or are there any new key technologies that make operating systems potentially dependable these days?
Well, I think if you look at the what I'll call commodity operating systems, Windows, Linux, the systems that we use very widely. If you think about them, they really were designed on architectures from the early 1970s. 30-year-old languages, 30-year-old operating system technologies. And it was a very different world than we live in right now. It was a world in which, for example, you either in the 1970s, if you had a computer, you either weren't connected to a network of any kind and never seen a network, or you were connected to a network that everybody else on the network was funded by the same funding agency as you. Okay. Whereas now you're connected to the internet with lots of people that not only aren't paid by the same funding agency, but some of them would like to separate you from your funding agency, for example, and your funds, right? Yeah. A very hostile world. Another place where I think things have changed very radically over the last 30 years is that 30 years ago, if you were using a computer and using an operating system, you were probably a graduate student or at least a computer science geek or something like that, right? And whereas now we have, so then you really wanted to know about computers, and now most people that use a computer, they don't have any clue how a computer works. They don't want to know how a computer works. They just want it to work for them. So our assertion is that, hey, if the world has changed that radically, well, then maybe the systems that we're using, well, they obviously don't fit very well, right? And we see this with all sorts of security problems and bugs and other things. And so that said, well, let's start over from scratch, thinking about what would a computer system look like that was designed for the modern world in its context.
Okay, so let's look at the solution, at the architectural foundations of the solution. Can you give us an overview of what these are?
So Singularity, as I mentioned, one of the probably the most important things is it is written in safe code from the ground up. So there's a whole class of errors that exist in current systems, buffer overruns, things like that don't exist in this system because they've been by design not allowed in the system. Singularity itself, as I already mentioned, it's a microkernel type architecture. So there's a closed kernel at the bottom that's sealed off, and then all of the code runs above the kernel in processes. And Singularity supports three kind of primary abstractions, I guess I would call them. So there's three core ideas in the architecture. The first one is what we call a software isolated process. The second one is that the communication between processes is through channel-based contracts, so with rich information. And the third one is an idea that we call manifest-based programs.
So if I were a buzzword person, then I would say this sounds like SOA, but I don't want to do this. but I mean, everything. Well, no, I'm not going this way. But there is clearly something which people often call as component-based software development, where where a component has a well-defined dependence or well-defined dependencies on its environment, and so it's not a surprise if you run a component what it wants from its environment. It's formally specified. So it clearly isn't that tradition, right?
Yeah, traditionally when you talk about component, a good way I would describe it is you have a piece of software and it has some dependencies, and those dependencies are expressed in a way that a human can understand them.
That's the traditional way.
That's the traditional way.
Yeah, right.
And in Singularity, with this idea of a manifest-based program and also the channel contracts, what we've actually done is specified the requirements in such a way that a computer can process them. And not just in the source code, but in the final binary. Yeah. We have this idea, a term that I use, which is a self-describing artifact. And the idea is I ought to be able to pick up a piece of software, the binary, look at it, and know exactly what its requirements are to run and how it interacts with the rest of the world.
So if you specify what this thing is and what it expects from the rest of the world, how far down do you go there? I mean, obviously one thing is easy. You can say, I want to communicate to this other thing, which maybe has a type. So that's relatively easy to specify. And then you have this concept of channels. So I guess your components say, I want to talk to this channel. But do you also formally specify something about the real behavior of the thing?
We aren't doing formal specifications. So the way I would answer that is we describe how you interact. So what
black box.
So like what so it's kind of a black box, but the channel contracts describe your behavior as another party would see it through this particular communication interface. But within you, we don't describe what happens inside. Okay. A good way I describe it is we'll say what we know what you're going to say and what are the ways that you can put language together, but we're not going to tell you how you're going to think.
Yeah, and what this means.
Yes.
Yeah. So the contract-based channels basically means that you specify message interactions, what goes in, what goes out, how you react to a specific message.
Yes. So we specify the contracts, specify the messages that are allowed to go across a channel of this particular type, and it also has a state machine that describes the patterns of the communication. So a good example of this is, most people would recognize pretty easily is when I access a file in a traditional operating system, I'll open the file. The operating system will say, "Okay, it's opened," and then I can do my read and write requests. And then when I'm done, I can say close. And, there's an implied state machine of I can't do reads and writes before I do an open or after a close. Yeah. And so this is just a kind of a formal mechanism that you can express those types of relationships. And it lets us do some very powerful, so we can actually compile these contracts. We can also take the binary for a program that implements a contract, say a client, for example, and we can analyze the code.
Oh, cool.
And we can detect if the client actually conforms to the contract.
So you don't do it with a runtime watchdog that starts shouting if you don't comply to the contract, but rather you can do this statically.
Yes, and so we can actually check it on the developer's desktop. So I have for me, a very fun story around this, which is we got the channel mechanism up and running and had Singularity running web server benchmarks for about a year before we had the verifier online. And when we got the verifier online, we loaded in the contract for TCP sockets. And talking with the TCP IP stack. And we ran it across the channel contract, and we found there was an error in the contract, so we fixed the contract. And then we ran it across the server code, our web server, and it turned out we had a case where we weren't handling what happens if the web server went to the socket, asked for data, and there was no data available. And it didn't correctly handle this case, so it was what we'd call a Heisenbug. So this bug had been in the code for literally a year. Okay, and we had never diagnosed it, probably never even realized it was there. Just had server runs that didn't run very well. We ran this verifier, and literally within like 2 minutes of when we started the verifier on the code, the verifier came up and said, "You have an error in this line of code. You aren't handling the case when there's no data."
Cool.
Okay.
Because the state machine basically had a state or a transition that wasn't followed.
There was a message in this state so there was 3 messages. Here's the data. The other end is closed to the channel, or there's no data. And we weren't handling the no data case. And this was the day that the engineers on the project, up until then, they had complained very vocally about these contracts, that they were in the way, they were a lot of work. And the day that we found one of these bugs, it was a very subtle bug, the engineers stopped complaining. And from then on, they've been very gung-ho about the...
It's interesting. We've had an episode a while ago on static analysis tools, and actually I forget who we did this with. Anyway, the guy basically explained that building these tools is quite complex because you have to understand what the code does. Now, I assume because you have the contracts formally specified in the state machine, so you do a lot of these things declaratively. So the analysis is probably relatively easy because it's clear how the communication happens. It's not just a side effect of something.
Yes. In fact, this was one of the key insights in the team. If you look at the composition of the Singularity team, you'll find that a large portion of the number of people involved in the project are static analysis, Jim Laris's software improvement group. So these guys that are world experts on static analysis. And one of the insights of Singularity, we said, we're going to create the operating system with the intent that we can do as much as static analysis at all. So we have contracts that are easier to verify. Not only do we have the world's best static analysis researchers, but
we also make their life easier.
We've also, that's it. We've done a good way to say it. We've done everything we could to meet them in the middle, the halfway ground as well.
Yeah, that's actually something I talk about a lot. I work a lot in model-driven software development and code generation, and I always say the more you can do declaratively as opposed to having it as a protocol somewhere in the code, the better, because all the stuff that's buried in the code is gone.
Absolutely.
Okay, so that was a long tangent. Anyway, let's look briefly about the software isolated processes. I mean, to me it sounds, well, I know that's probably not the case, but you could argue that sounds like overhead and sounds like it's slow because there is all this stuff in managed languages, and the switching context overhead might be worse compared to native low level stuff. So do you have any comparison with regards to performance?
In fact, it's faster. Okay. So the key thing, so let me drill in and explain the software isolated process a little bit more. So in a traditional operating system, you think of a process as a set of pages. And then the operating system uses hardware protection mechanisms to keep you from using a pointer to touch another process's memory. When it's software isolated process, what we do is we take the code. The code has to be written in a safe language, and we verify that it is statically, that it is incapable of generating a pointer to someone else's memory. And so then we can run the processes without any hardware protection at all, replacing the hardware protection with static verification. So we actually have a research paper that's on the website where we did a detailed analysis of what the cost of hardware is. And guess what? This hardware protection that you always thought was free, in fact, isn't free. It costs you, depending on the scenario and how you're using it, anywhere from 3 to 38% of your performance is used up. In fact, in the minimal case, just turning on the TLB, the translation look-aside mechanism from physical to virtual to physical addresses, costs you on the order of about 3% of your performance. Okay, and so we are able to get rid of all those the overhead of the hardware. We're also, when you talk about a context switch, we don't have to change address spaces and reprogram the hardware when we change contexts. And so actually our context switches are between 5 and 10 times faster than traditional operating systems.
Cool. The last thing we didn't talk about explicitly is the manifest-based program.
Again, the key idea with these manifest-based programs is getting back this idea of a self-describing artifact.
Yep.
And being able to analyze not only individual programs, but the entire operating system. So even the kernel in our case has a manifest.
Cool.
And what this allows us to do is we can take the entire system, and when you come and try to install a new program, we can tell you at install time if it's going to break compatibility or interact in a bad way with any other part of the system.
Versioned, I guess, so there's the notion of a version.
Very rich versions.
Yeah.
And we also have very rich dependency information. So you can literally ask a question before you ever run the code. You can say, is this program capable of running correctly on my hardware and software configuration?
So something we should probably tell our listeners is that there is a really nice paper you wrote, and that's what I read somewhere on the web, and that's the basis for this interview. So I read about the SingSharp language.
Yes.
So what language support do you have? Probably it's built on top of C#, I guess. So what's in addition to C# in that language?
So there's actually 3 languages involved here. Okay, so SingSharp is built on top of a language called SpecSharp. That came out of Wolfram Schulte's group here in research, which is built on top of C#. Okay, so SpecSharp adds pre and post conditions around functions.
I read that somewhere.
And invariants, you can put in object invariants. And then what SingSharp adds to SpecSharp on top of that is first-class mechanisms for talking about communication. So sending and receiving messages and operations around communication are first-class operations. There's also support for what we call linear types. So in Singularity, when you communicate, there's no shared memory between processes. You communicate by exchanging memory.
Yeah, sure. Yeah.
And there's a mechanism that we can use. It's called a linear type. And what that means is the easiest way I'll describe it is only one person can hold a pointer to this piece of memory at a given time. And so when you give the memory off to someone else, we can actually look at your code and know that you're never going to try to access that memory again. So it makes it so we can do very cheap communication.
So that's the point, because if you do message passing in traditional systems, you physically have to copy the stuff, and that's big overhead. And what you do is you avoid that. You have basically exchanged the pointer, but you are sure that nobody can mess around once you hand it off.
That's right. And so it allows the communication to be extremely cheap and also statically verifiable.
Right. And because it's all in one big process, because you isolate via software and not via machine process things, you actually can share the memory.
Yes.
It reminds me a little bit of Erlang, the Erlang language.
There are some similarities with Erlang.
I recently talked to Joe Armstrong about it.
Okay.
What's the process you work? You've probably first describe your contracts, and then you, I would guess, generate some kind of skeletons against which you then implement the component, or how does this work?
Well, so you specify your contracts first, and you write them in. That's the other thing that the SingSharp has is the contract language is actually SingSharp.
Yeah.
So you write it, just like you're writing structs or something.
Yeah.
Here's my set of messages.
Yeah.
Here's the channel contract, and then from a piece of code, you in your C# code, you import that namespace that contains the contract, and then you can just use it and program against it.
Okay, because it's all based on the CLR, and so there's no code generation involved there.
That's right.
What is the role of the kernel? Actually, we in SE Radio, we didn't have an episode on operating systems yet. Maybe we should. So can you briefly explain what the kernel does and how it's different from traditional kernels, if there is a difference?
Okay. Well, so in a traditional kernel, a traditional operating system like Windows or, say, Linux, the kernel does everything. Okay, the kernel knows how to talk to the disk. The kernel has the file systems. The kernel has the network stack for sending messages. The kernel hosts all of the device drivers. And then the kernel does basic things like providing access to memory, scheduling threads, managing resources, and things like that. Singularity is what we call a microkernel design. And it's an old, the idea of a microkernel is pretty old. It dates back to relatively old. It dates back to the 80s with Mach and some other systems. Your European listeners should recognize L4, for example, as one of the key microkernels. Anyway, if they know operating systems. Singularity. So what this means for Singularity is that the kernel in Singularity provides some very basic services. It provides the ability to create processes and shut them down, the ability to create threads of execution within processes, the ability for processes to acquire and release memory when they need it. And it also contains the ability to send and receive messages to other processes.
So it dispatches them, or is it like just another component which others can talk to?
The abstraction that we present is a channel endpoint.
Right. Yep.
And then the kernel mechanism is you can send a message on an endpoint, and the kernel manages the transfer of that message
like an orb in some sense.
Yeah. Okay. To the other
right.
process, and then you can receive a message, which is to take the message out of the
right.
channel.
Yeah.
Okay, and it's that portion is actually very, very lightweight. But so it's a fairly minimal kernel, and then all of the services that you particularly think of, operating services, so the network stack, the file system, the device drivers, run as separate processes, as SIPs, these software isolated processes up above the kernel. And one of the key benefits of that for Singularity is if you think about a traditional system like, say, Windows, device drivers run in the kernel space. And so they're just bits amongst the rest of the kernel bits. And so if a device driver fails, the whole kernel goes the blue screen of death, right? Well, one of the things you find is that device drivers are much more prone to failure than, say, kernel code, okay? In Singularity, these device drivers run in separate SIPs, and so if a device driver fails, we can just close it and start up another one, for example.
So you mentioned it before, the kernel is written in C# or Sing#, not in C or assembly language, or is there a little...
Well, so the way I described it is the primary language we've implemented is C#. Okay. So I always say C#. It's actually Sing#.
Sure. Okay. Plus your contract stuff.
Plus these contracts and things. And the way to say it is 95% of, by line count, 95% of the kernel is written in C#. And then we still have assembly code, basically the same place. If you looked at, say, the Linux source code, you'd see that most of it's written in C, but there's places where there's assembly. So like the context switch code for thread context switch, interrupt vectors at the bottom and things like that are still assembly.
Another abbreviation that sounded to be quite central is ABI. What's that?
ABI is, that's a funny one. Everybody always asks me, what does ABI mean? It's actually a very old term, particularly from the Unix world, and it means an application binary interface. And what it means is it's a very formal description of the interface between a program and the kernel. Okay. So typically in historical Unix contexts, it means, what is the binary format of a program? What is the syscall interface between the program and the kernel, et cetera? And in Singularity, we likewise have a very concrete kind of formal description of what the interface is between a program and the kernel. So what are the services that a program receives from the kernel?
Sounds to me like channels or endpoints.
It's a very good question. Here's the simple way I can answer that question, because in fact, in some of our academic papers, some of the comments that come back is, well, why aren't you using channels for everything? Why is this a kernel ABI? Here's a simple reason. If I send a message on a channel, there has to be some way for me to tell the kernel, okay, send this message on this channel. Okay, so there's some basic primitive operation, send and receive. Okay, those are exposed as ABIs. Singular, actually, there's more than just that, and I think it's one of the very unique aspects of the Singularity design is that the ABI, the way I would describe it is it gives a program a guaranteed subset of functionality around pure computation.
Mm-hmm.
I can create threads, I can run threads, I can synchronize threads, I can get memory, and I can communicate with other processes through SIPs. And that set of functionality is always available to any program, regardless of which version of Singularity it's running on or what other services might be there. It also means that you can always count on it. And it also, one of the things that lets us do very, very easily is sandboxing.
Mm-hmm.
Okay, so Windows, for example, or Linux has a very hard time with how do I run a piece of code like some random code that I bring off the internet that I want to be able to say do computation, but I want to know it's not going to go talk to my file system or send spam or anything like that. Well, that ABI lets you give a base abstraction for everything you need for a language runtime to run. And then we can give you channels for the additional things that we want you to do. So if we want you to be able to draw to the screen, we'll give you a channel to the screen.
Yep.
If we want you to be able to talk to the file system, we'll give you a channel to a file system or a subset of it.
And one of the important words you mentioned was give you. So you cannot just grab a channel. You have to declare it probably somewhere, and then you're given the channel.
Yes.
And the giver decides whether this is maybe just a mock or whether it's the real thing. And
yes.
so
That's
managed.
exactly the case. And so the giver can decide. And so, and it does have to be declared in your manifest stat. And not only does it have to be declared in your manifest, but we also take your binary and we'll analyze it, at install time and make sure that you aren't hiding in some place in your code that you're going to try to talk to, say, the TCP/IP stack to send spam, for example.
Yeah. So there is this other thing called capabilities that I have to kind of make sense of in that context. Is that something we already covered, or?
The short answer is that channels are capabilities. Okay, if I give you a channel endpoint, I'm giving you the capability to communicate with somebody. Okay, and so this allows us to use Singularity as a capability type system, where I can talk about a program has these capabilities because I've given it this endpoints.
Okay, one last question about this core stuff. You mentioned that SIPs have threads. Now, SIPs sound to me relatively lightweight. Why do you need threads? Why not have just hundreds of thousands or whatever of SIPs, of processes?
That's a good question. So actually, our threads are even lighter weight than traditional threads. They don't have to have they have a mechanism we call link stacks, for example. So they're very, very lightweight. They're even lighter weight than SIPs. The answer to that is, well, we think that there's quite often the case that people, in order to express parallelism, that they need shared memory.
Yep.
And so, and since we don't allow shared memory between SIPs, the only way to do that is inside of a given SIP with threads.
So the argument that they have shared memory and therefore are faster than processes doesn't really count, because you have shared memory, at least on the exchange heap, between processes.
Yeah, but except for, I'll be very clear with this. When we say the exchange heap is not shared across time.
Well, from a performance perspective, it's shared,
from
but the programming model is different.
That's right. From the performance perspective, it's like shared memory.
Yep.
From the correctness perspective, we always guarantee that only one SIP can access that memory at any given time.
Yeah, very nice. Okay, so this was kind of the core of the system, and you mentioned obviously before that this is still a research system. So you also do exploratory. Well, you do experiments based on that platform. And so can we look a little bit about what some of these experiments are? One thing you've mentioned in your paper is compile time reflection.
Yes, so that's what was one of my favorite experiments. So one of the things that we say in Singularity is that the processors are sealed. Okay, so this means when we start up a process, before you start the process, you have to name all the code that's going to run in that process. And once you begin execution, you can't alter the code that's inside that. You can't add new code, for example. And we also, the other thing we do is I think I mentioned already, is even though we write the code in C#, we're not a just-in-time environment like the JVM or like the CLR. We're actually a ahead-of-time compiled environment.
Okay.
So at install time, when you install a program, we take the MSIL, the intermediate language from the CLR, that the C# programs are compiled into. We take that MSIL and we compile it into the native instruction set of the processors on your machine.
Yep.
And so this makes traditional dynamic reflection fairly difficult.
Yeah.
And so we came up with this alternative mechanism we called compile time reflection. And basically the idea is if you look at the way people use reflection, almost like 90% of the uses of reflection are for marshalling and interprocess communication and serialization and things like that. And that stuff doesn't really need to be dynamic.
Sure.
The way to think about it is a human has expressed their intent before that code runs.
Yeah.
And so what we've done is we've given a mechanism called compile time reflection where the programmer can say, hey, for example, if I'm generating marshalling code, here's what the marshalling templates look like.
Mm-hmm.
And then we actually, when we compile, we go and generate all the code instead of doing it dynamically.
Yeah. So for that, to do that, the Sing-Sharp language has this transform primitive or this transform thing.
Yes, that's right. And basically, you build some templates and you say, here's you have a matching template. So this is, whenever you see a pattern that looks like, say, a class that has this serialized attribute, then you have a template and say, then generate this body of code.
Sure.
So it typically looks like, if you find a class has a serialized attribute, generate the write to stream method. And here's what the body should look like.
And because it's compile time, the nice thing is that if in subsequent code you actually call this automatically generated method, the compiler will not complain because at that time the method is actually really there.
That's right. The method is really there. And it's also much faster than if you do it dynamically.
Sure, yeah.
I did some experiments. I actually do not remember if we ever published this result, but I actually did an implementation on the CLR communication between two app domains in the CLR.
Yeah.
One using the CLR's built-in remoting, and the other one using compile time reflection. The compile time reflection one is 50 times faster.
Yeah, I believe that. Yeah. We actually had an episode a while ago with Lawrence Tratt about his Converge language, which also supports compile time metaprogramming, compile time macros. So that ties in nicely.
Yeah, it's a very active area of research.
Absolutely, yeah. So you already said that there is this possibility of adding an attribute to something and then automatically transforming that into code. So that's probably, so the question is how is this metaprogramming thing used in the platform? How do the manifest-based things, how does that go together?
So in fact, the very first place that we applied it, in fact, kind of the motivating scenario for doing the compile time reflection was for the device drivers. So if you think about a device driver, if I'm a video device driver, I have a set of resources that I want from the hardware. I want access to the I/O ports for that device that I'm the driver for. I want access to the memory buffers and other things like that. And traditionally, the way this is done is when your device driver starts up, it goes off and it asks for these resources and interacts with the operating system dynamically to ask for the resources. Yep. And there's, as a side effect, if you pick up the code for a device driver, the binary in a traditional operating system, you can't say anything you have no idea what the dependencies are. Okay. Well, in Singularity, what we do is we actually there's an object that you build into your device driver that has a set of attributes, and you label explicitly what are the resources you want as objects with labels, and then you just use that object. You never ask for your resources. Okay, as you express your code, you just use those resources. And then what happens is, we read your binary, we create the manifest for your binary, and then we use the compile time reflection to generate all the code that knows how to, given some operations from the kernel, to give you access to those resources. And so we can check all your dependencies, but we give you this added benefit of, we generate this code for you automatically.
Sounds a bit like dependency injection in some sense. I mean, you specify what you want explicitly, formally, machine readably, and then you have some external power which reads the stuff and gives you what you need.
That's exactly what happens.
Yeah, very nice. I mean, I have a little tangent here. I mean, I've been talking about this model-driven component-based development for ages, specifying in models what a component does and all this stuff. So to me, what you do here is really taking this to the right level, making this the operating system paradigm as opposed to having that somewhere in a system. So to me, this is really absolutely cool. I really like it.
We're trying to be cool. So. That's what we're trying to do. So.
I'm not sure that it's necessarily cool to the general public. I mean, it's not a hype topic.
Yeah,
you should call it SOA-based.
It's hard to explain it to my wife. I'll give you that.
Okay. So, and one of the nice things of compile time metaprogramming as opposed to runtime is, of course, also that your static analysis tools and your dependability analyses work on the result of the metaprogramming transformation steps.
That's right.
You can't cheat.
Yeah, and in fact, the templates are specified in such a way we can statically check the template and know that it will only ever generate valid code.
Yeah.
Whereas, say, if you use dynamic reflection, it's a very low-level interface, and there's no way to tell ahead of time that the code will be correct.
Yeah. Okay, let's look at another experiment. And everybody knows that the world is going to be radically different in a couple of years because we all have 55,000 different cores on the processors. So this whole thing of multiprocessing, SMP, multi-core is probably something you couldn't have ignored when building Singularity.
No, we couldn't have ignored it, and in fact we found a few opportunities. So the base Singularity system is multi-threaded, multi-core. So give it 16 processors, and it's just happy to chunk away and use all of them. But we've also done some experiments around this idea of that we call heterogeneous multi-core. Mm-hmm. So if you look at if you have 55,000 processors on your machine, just to pick a random number. We don't think they're all going to look the exact same, okay? There's lots of reasons for power consumption or resource utilization. Do you want to actually have different sets of cores if you've got that much hardware? And so one of the things we've been looking at is how do we make a programming model that lets you express your program and run it, and if you have 15 different types of cores in there that we can use them. A good example is we can let you build a program that's able to use your GPU and your CPU and, say, a special processor on your I/O cards simultaneously. And you don't have to worry about, well, how do I program a GPU? Just write the code, and we manage to generate the right code to run on the GPU for you. The other thing that we've done in this experiment is an idea that we call a subservient kernel. So you find if you look at these many core systems, so if you have 55,000 cores, to pick a random number, they're not all going to have the same size cache as we have on current machines. The caches tend to be smaller. And so that means the amount of code you want to run on that particular core, you want it to be smaller. Okay. And so we came across this idea of, well, a lot of these cores don't need to actually run very much of the operating system. In fact, they might want to run just a very, very small sliver of the operating system. And this thing we call the subservient kernel. And we can scale it everywhere from it's a pure kernel that runs side by side with the other kernel just on separate cores, or down to a very small kernel that's about 12K in size that doesn't do anything other than forward request to a master kernel on another processor.
The other thing I read about was hardware protection domains. So although we discussed, or you mentioned that you do everything software isolatedly, there is still some hardware thing in there. So why and what does it do?
Well, so one of the questions we got asked when we were going around and giving the academic talks on Singularity is, is hardware protection really that expensive? Or what if I run out of address space because you're sharing it with all the processes? So we added this idea of a hardware protection domain, and it is a hardware-based protection domain. It's an address space, okay? So the way you could think of it is almost a traditional, heavyweight hardware-type process, and we can generate them as a runtime decision. You can say, I want to take this SIP or this set of 5 SIPs and place them into a hardware protection domain. So, for example, if you have a SIP that came from the outside world, from some hostile entity, you're not sure what it's really going to do, but you really need to run it, you can put it in one of these hardware protection domains and get an extra level of protection. Or another example is a piece of code like SQL Server wants to have lots of virtual memory, and so you can give it its own virtual address space. And so we can have hardware protection domains or separate address spaces, and they can be either privileged, so they run at the same protection level as the kernel, or as user mode. So we can, so you can either look at it as belts and suspenders, or a way to be able to expose more rich capabilities out of the hardware, but not have to. The key thing is you can use it when you want it, but if you don't need it, you don't have to pay for the cost.
Yeah. You also have a typed assembly language, which to me almost sounds like an oxymoron. So, so what is that about?
So typed assembly language is about this. So remember we were saying we're relying on static verification to provide protection. So, so we take MSIL code and we convert it to x86 code. And in Singularity, as originally conceived, without typed assembly language, what that means is essentially the compiler is part of the trusted computing base. If the compiler messes up and lets the programmer manipulate memory incorrectly, the security of the whole system's been compromised.
Yeah.
What typed assembly language lets you do is the compiler, in addition to emitting the assembly code or the machine operations, also emits a proof that the code that it's generated is type safe.
Mm-hmm.
And then when you load in that binary, there's a very small checker. It's on the order of a few thousand lines of code that checks the typed assembly language to make sure that it is in fact type safe.
Mm-hmm.
And that allows you to take the compiler out of the trusted computing base. So anybody can build a compiler. They can build a compiler for whatever instruction set or they want, but we can still verify it and still have safety.
Assuming that other compiler also outputs this metadata that you use for proving things.
Yes.
Yeah. Okay, so we're coming up towards the end, slowly but certainly. So let's think about a couple of concluding thoughts. We already talked about the performance of this thing a little bit.
It was an interesting thing with the performance. When we designed the system and when we were originally planning it, we said, dependability is far more important than performance.
Mm-hmm. Absolutely.
I think there are people that would be happy to have a computer that was 20% slower if they knew that they were never going to get another virus, for example.
Especially since next year it's going to be as fast as now.
Yeah, exactly. And so we set off saying, we're not going to care about performance. It needs to be fast enough that people will use it, but it doesn't need to be the fastest operating system on the planet. And we were very surprised when we got the full thing up and running that, in fact, it's got very good performance because of the software isolation, for example. So this dependability actually buys us some performance in some cases.
Mm-hmm. Mm-hmm.
So it's a pleasant surprise, but not, even if it wasn't the case, I think the system would still be a success.
Mm-hmm. Yeah, absolutely. Sounds like it. But compatibility with current operating systems probably doesn't really exist. I can't run my Windows
There is
thing.
no compatibility whatsoever.
But that's maybe a good thing for a change. I mean, we have to start at some point again.
Well, there's I guess, so we do have one form of compatibility, which is if you have C# code that runs on the CLR, you can run it on Singularity. It's kind of like porting between different versions of Unix. If you're high level, you just run the code. If you've mucked around low level, it's not. I guess the compatibility really gets back to the core idea of this is a research prototype. My job as an operating systems researcher at Microsoft is to try out radical new ideas as far out in the future as I can. See which of those ideas work. The ones that work, I come back to the product guys and I say, hey, you should come try to incorporate these ideas into your product. And they can figure out how to do compatibility. And, and then the other thing is sometimes we produce negative results. In fact, Dan Ling, our former vice president, used to say, if we don't fail half the time, we're not being aggressive enough.
Yeah.
So when we fail, we go to the product guys and we say, hey, we tried this really aggressive thing. It's not going to give you the desired results. So don't go down this path at all as well. But anyway.
So is there any interest from the product group? Is it going to be in Windows 2012 or something?
Well, so the way we do tech transfer most of the time at Microsoft is we don't pick up, say, the entire code base and say, okay, Singularity is going to be the next version of Windows, for example. What we do is we transfer as many ideas. And there are already ideas filtering out into the product groups and the CLR team and into the Windows team.
Cool.
And some of the ideas will get out there sooner than some of them will get out later. But I think we've had a much stronger impact than I anticipated we would when we started the project.
Mm-hmm. So to wrap this up, since we're talking about ideas and concepts, I think one other conclusion from this project might also be that the combination of a good architecture, good concepts, a language that has those concepts as first-class citizens, and the useful tools for it, for example, the analysis tools, that these three building blocks are probably a very good set of ingredients for building really good systems.
That's exactly the message.
And of course, I didn't come up with that. It's in the paper. But I really like this message. And it's not limited to operating systems.
Yeah, I think it's very true. I think the ideas can be applied in lots of places. When we started the project, one of the key ideas was particularly around the static analysis and the verification tools. And the tools people in the research and the product groups as well have made tremendous progress over the last decade, and it's great to see those tools getting applied.
Yeah. Okay. Is there anything else I should have asked, or some pearls of wisdom that you want to leave with our listeners?
I've got no wisdom whatsoever. However, I did want to say one thing. So we've been talking here with me, one person, and this is Singularity was actually the product of a large number of people. We had about 30 researchers in Microsoft research involved across both our Redmond lab and our Silicon Valley and our Cambridge labs as well. It's been a fantastic experience just working with some of these best researchers in the entire world. Yep. And I'm just thrilled to death they let me work with them as well.
Absolutely. So thank you and all the others for sharing this with us. I think this was for me, it was a really inspiring paper and episode. Thank you.
Thank you.
Thanks for listening to Software Engineering Radio. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@seradio.net, or if it's specific to an episode, please use the comments facility on the website so other people can read and react to your comments. This episode of Software Engineering Radio, as well as all other episodes, are licensed under a Creative Commons license. Please see the website for details. Thanks to Charlie Crow and the PodSafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.